Good morning, students. Today I'm going to teach you the next topics of Lebesgue integral. This is unit 3rd of measure theory and integration. These are the topics which I have already discussed with you. The first one is the Riemann integral in the terms of step functions. How to define the Riemann integral in the terms of step function. The next is the elementary integral and their properties. The third is the Lebesgue integral in the terms of simple functions. And fourth, we have done the comparison between the Riemann and Lebesgue integral. That means Lebesgue integral is an extension of Riemann integral. And the next is very important, that is the connection between Lebesgue integral and measurable functions and the properties of Lebesgue integral. So the today's topics are the properties of Lebesgue integral with the corollaries, related examples, the theorem. In the last lecture, I have already discussed this theorem that f and g be bounded measurable functions defined on a set E of finite measure, then the following properties hold. Means the integral of a times f is a times integral of f over e, where a is any constant. Integral of f plus g over e is same as that integral of f over e plus integral of g over e. If two functions are same almost everywhere, then their integrals are same. If f is less than equal to g almost everywhere, then the integral of f is less than equal to integral of g over e. And if function is bounded, it lying between some fixed numbers, then the integral is also bounded, it lying between alpha times measure of e and beta times measure of e. And the last property, if E1 and E2 are disjoint measurable subsets of E, then the integral of f over E1 union E2 will be integral of f over E1 plus integral of f over E2. Now based on this theorem, we have some corollaries. The number one corollary is whenever the function is greater than equals to 0 on the domain, then the integral is also greater than equals to 0. Similarly, if it is negative, then integral is also negative. This is by the property D. The converse of part C need not be hold. What is the converse of part C? Converse of part C is if two integrals are same, this does not imply that f is equal to g almost everywhere. For example, if f and g both are the functions on the same interval -1 to 1 and they are defined like fx is 2 when x is negative, it is 0 when x is positive, and gx is 1 for all x, then the value of integral of fx over -1 to 1 will be 2, which is same as that integral of gx. How to evaluate this integral? You can split this integral from -1 to 0, the value of function is 2, plus from 0 to 1, the value of integral is 0. So you can substitute the value of fx over here and you can integrate it. We will get the value of integral is 2. Similarly for gx is 2. These two integrals are same. However, fx is not equal to gx for at least one point. They are not same. So that means the converse of the property C need not be hold, that whenever two integrals are same, that doesn't imply that the functions are always almost equal. The next example shows that the converse of the corollary need not be true. Other two corollaries are, if measure of E is 0, then integral of f will be 0 over that set. So means integral of any function over set of rational number will be 0. Why? Because the measure of rational is 0. The next corollary is, if the function is constant almost everywhere on E, then the value of integral will be k times measure of E. This is by the property E. In this case, the value of the function is k almost everywhere. So the value of integral will be, you substitute the value of function over here, this is k into integral of 1. Integral of 1 is nothing but the measure of E. So in particular, if you take f to be 0 almost everywhere, then the integral of f will be 0. And if you consider f to be 1, put k to be 1 over here almost everywhere, then the integral of 1 is 1 times measure of E, means measure of E. So value of integral of 1 is nothing but the measure of that set. This is an example which shows that the converse of this corollary need not hold. Means the value of integral of f is 0 doesn't imply that the measure of E is always 0. Or you can say function is 0. For example, we consider the function f on the interval -1 to 1 by 1 when x is positive, -1 when x is negative. And if we evaluate this integral, we will see this will be 0. However, neither our function is 0 almost everywhere, nor the measure of E is 0. Measure of this set E is 2, which is the length of this interval. So that means integral of f0 does not imply that the measure of E is 0, or integral of f is equal to 0 does not imply that f is equal to 0 almost everywhere on E. Okay, so converse of above corollaries need not be true. Now this is the converse of above corollary, which says that if integral of f is 0 and the function is greater than equal to 0, then f will be 0 almost everywhere on E. So there is one more condition, that function should be greater than equals to 0 on E. Only then we can say f is 0 almost everywhere. Statement is clear. Once again, see what is given to us. Integral of f over E is 0 and function is positive on E. We have to show that f is 0 almost everywhere. To prove this, we first consider a set A, which is subset of E, such that it contains all the points E where fx is strictly greater than 0. There are two possibilities for the function. Either function is 0 or function is strictly greater than 0. So we consider set A to be those points where the function is strictly greater than 0. We can write also this as a union of all those x belonging to E where fx is strictly greater than 1 by n. Means those points of V where fx is greater than 1, those points of E where fx is greater than half, 1 by 3, and so on. Take the union of all these, you will get this set. So this is same as that this. So now what we want to show? We want to show f is 0 almost everywhere. Okay. So it is enough to prove that the measure of this set A is 0. If measure of A is 0, then this implies f is 0 almost everywhere. Why? Because here are only two possibilities. Either function is strictly greater than 0 or f is 0. But if we show that at those points where f is greater than 0 has the measure 0, means f is 0 almost everywhere. Okay, so it is enough to prove that the measure of each sets in the union is 0. So what we want to prove? We want to prove that the measure of each such set, which set? All those x belonging to E where function is strictly greater than 1 by n. The measure of this set is 0. Let if possible, for any natural number capital N, this measure is non-zero. Say it is lambda. So we can split the set E into two sets. One is E1, the second is E2. E1 set contains all those points of E where this function value is strictly greater than 1 by capital N. E2 set is those points where function is less than equal to 1 by capital N. So clearly these two sets are measurable and disjoint, and its union is E. Okay, so thus E1 and E2 are two measurable disjoint sets such that E is equal to E1 union E2. So therefore, integral of f over E by the last property, the integral of f over E1 union E2, where E1 and E2 are disjoint, is the integral of f over E1 plus the integral of f over E2. Now just see what is the value of integral of f over E1. On E1, the value of function is strictly greater than 1 by n. So replace the value of fx. Over here we can replace f with greater than 1 by n. So we will get integral of 1 over the set E1 into 1 by n. Now this is nothing but measure of E1, and measure of E1 is lambda. So we will get integral of f over E1 is greater than equals to lambda by n, which is strictly greater than 0. Now why capital N is any positive number? Lambda, it is also non-zero positive number. As we know that measure is always greater than equals to 0. This is non-zero number, so it should be positive. It should be strictly greater than 0. So what we get? We get the integral of f over E1 is strictly greater than 0. If this number is strictly greater than 0, this is also some positive integral. Now why? Since the given that function is greater than equal to 0 on E, this implies integral of f is always greater than equal to 0 by the property D. Okay, so this is positive integral, this is positive integral. It may be 0, but we have shown that integral of f over E1 is strictly greater than 0. So ultimate the value of integral f over E is also strictly greater than 0. which contradicts to the given hypothesis that integral of f is 0 over E. Okay, so that means our supposition is wrong, which we have supposed that the measure of all those x belonging to E where the function value is greater than 1 by n is non-zero. This is wrong. So it should be 0. So that means measure of such sets are 0. So this implies the measure of A is 0. So if measure of A is 0, it means f should be 0 almost everywhere, because where the f is greater than 0, that has measure 0. So thus f will be 0 almost everywhere. The next theorem, this is very important result which tells us how we can interchange the limit and integral operation. This is named theorem. This is bounded convergence theorem. This says that let Fn be a sequence of measurable functions defined on a set E of finite measure. Suppose there is a real number capital M, that this whole sequence is bounded and this sequence is converging pointwise to a function f. Means fx is the limit of this sequence fn for each x belonging to the domain. Then this theorem says integral of f is same as that limit integral of fn. That means we can interchange the limit with integral. Once again, see what is the statement. Let Fn be a sequence of measurable functions defined on E with finite measure. Let this sequence is bounded and pointwise convergent. Then integral of f is same as that limit integral of Fn. Now the proof. Since the function f, it is the limit function, each fn is measurable, so this implies limit function is also measurable, so fx is also measurable function. Each sequence is bounded, so this implies limit is also bounded by m. So this function is bounded, defined on a set E with finite measure and measurable. So we get this should be Lebesgue integrable. We have already done the relation between integrable function and measurable function. This is just by that. Whenever we have a bounded measurable function on a finite measure, then that implies f is integrable. So here f is measurable, bounded, defined on a set E with finite measure, therefore f is Lebesgue integrable. Now by this theorem, I will explain in the next slide. This theorem says whenever we have a sequence of measurable functions defined on a set E of finite measure, pointwise convergent, then for given epsilon there is a measurable set A, subset of E with measure of A very small. Then there exists capital integer n, positive capital integer n, such that fnx minus fx is less than epsilon for all n greater than equals to capital N on E minus A. Once again, see what this theorem says. Whenever we have a sequence of measurable functions defined on a finite measure, and given that this sequence is pointwise convergent, then for some epsilon greater than 0, we always have a set A which is subset of E with very small measure, such that on E minus A our sequence is converging uniformly. Now here it is true for every x simultaneously, that fnx minus fx is less than some epsilon. So now in this case we choose delta to be this number, epsilon by 4m, and epsilon to be this number, epsilon by 2mb. Now why, we will see further why we take this number. Now what is given to us? Given to us the sequence is bounded for all x and for all n. So this implies limit function is also bounded for all x. So this implies fnx minus fx mod will be less than equal to this mod plus this mod, but this is less than equal to m plus m, which is 2m for every x belonging to E. So in particular this will be true for every x belonging to A. Therefore, consider the integral of fn minus the integral of f over E. By using properties, we can write this as fn minus f integral over E will be less than equal to integral of mod of fn minus f. Okay, so this mod will be replaced with this inequality. This is T property. Now further we can split E into E minus A and A. These both are disjoint sets. So we can split this integral, and this will be equal to the integral of this function over E minus A plus the integral of this function over A. Now just see, over A we have already shown that mod of fn minus f will be less than equal to 2m. So substitute the value of this function over here. Over the set A, this value is less than equal to 2m. So we get 2m into integral of 1 over A, which is nothing but the measure of A. Now over the set E minus A, this is given to us that mod of fn minus fx is less than epsilon by 2 measure of E for all n and for all x E minus A. So on the set E minus A, this value is less than epsilon by 2 measure of E. So you replace the value of mod of fn minus f with epsilon over 2 measure of E. So we will get the integral of 1 over E minus A, which is nothing but the measure of E minus A. So now just see, epsilon by 2 into measure of E minus A upon measure of E, it will be less than equal to 1. Why? Because E minus A is a subset of E. So measure of E minus A will be less than equal to measure of E. So this number is less than 1. Also we have to choose measure of A in such a way so that we get epsilon by 2. So that's why we put measure of A to be less than epsilon by 4m. So when you substitute the value of measure of A over here, you will get epsilon by 2. So that's why we choose measure of A to be epsilon by 4m. Okay, and this to be epsilon by 2 measure of E, so that this will become less than epsilon by 2. So both these terms are less than epsilon by 2. This term is less than epsilon by 2. when you substitute the value of measure of a from here, you will get this is also less than epsilon by 2. So epsilon by 2 plus epsilon by 2 will become epsilon. And this thing is true for all n greater than equals to capital N. Okay, so we get this inequality that the mode of integral of fn minus integral of f over e is less than epsilon for all n greater than equals to n. So this is by the definition of convergence. When a sequence minus the limit is less than epsilon for all n greater than equal to n, it means the sequence converges to this number. So what we get, the limit of n going to infinity, integral of fn is nothing but the integral of f over e, and this thing we have to prove. So once again, see, bounded convergence theorem says whenever we have a bounded convergent pointwise convergent sequence defined on a set of finite measure, we can always interchange the limit with the integral. Okay. Mainly we use this theorem in the proof of bounded convergence theorem. So we split the set E into two parts. One is E minus A, other is A. On A we will use the bounded, and on E minus A we will use this thing. Combine these two, we will get the sequence converging to F on E, and this is the proof. A slightly improved version of this is given by, let Fn be a sequence of measurable functions defined on a set E of finite measure. Suppose the sequence is bounded. If Fn converges to F almost everywhere, then F is integrable, and integral of F is nothing but the limit integral of Fn. So what is the difference between this and this? Here we are given it is converging to Fx for each x, and here it is given Fnx converging to F almost everywhere. So at those points where the sequence is not convergent, that points have measure 0. So means integral remains the same. So proof is on the same lines. Rather taking set E, we will consider the set E1 where this sequence converging to F for all x belonging to E1, and those points where it is not convergent, the measure is 0. So integral becomes 0. Okay, so you have to do this theorem by considering E1 subset of E. At E minus E1, the measure is 0. Clear to everyone? Now I am going to prove this theorem. Now, this is a theorem which is very important, which gives us a relation between pointwise convergence and uniform convergence. This is in unit 2. Let E be a measurable set with finite measure, Fn be a sequence of measurable function defined on E, F be a measurable real valued function such that our sequence converges to Fx for each x belonging to E, means pointwise. Then this theorem says, given epsilon and delta greater than 0, there is a measurable set A, subset of E, with measure of A less than delta and positive integer capital N, such that Fn minus Fx, this is less than epsilon for all x belonging to E minus A, and for all n greater than equals to capital N. Means here what is given to us, Fn minus Fx is less than epsilon for each x belonging to E. Means your F1x, when you consider x to be x1, F1 at x1, f2 at x1, f3 at x1, this will become one sequence which converges to f at x1. When you change the point, it will converges to that point, right? But here it is true for all x simultaneously on the set E minus A. Means at A, this sequence is not convergent simultaneously, uniformly. But over the set A, the measure is very small. So whenever we have a measurable set with finite measure and a sequence of measurable function converging pointwise to a measurable function, then we always have a set E minus A where the sequence converges uniformly, with the condition that the measure of A is very small. So to prove this, we first consider the sets Gn. Now what is Gn set? It is a set of all those x belonging to E where mod of fnx minus fx is greater than equals to epsilon. So we take the reverse of this and we will show that the measure of this set is 0. So we get this thing, right? So we consider a set Gn, all those x belonging to E where this value is greater than equal to epsilon. Now since f and f both are measurable, so difference of two measurable function is again measurable. So we will get Gn is measurable. Now we define a set Ek, which is a union of Gn where n varying from k to infinity. Means what? E1 is the union of 1 to infinity of Gn. E2 is the union of 2 to infinity. So clearly Ek is a superset of all other sets. So Ek plus 1 will be a subset of Ek. Means our E1 is the bigger set. E2 is contained in E1. E3 is contained in E2. This is decreasing sequence. Right? Now what is Ek set? Substitute the value of Gn over here. It is a set of all those x belonging to Gn. Now union means it is true for n greater than equals to k. That means all those x belonging to E where fnx minus fx mod is greater than equals to epsilon for some n greater than equals to k. Due to union, we get for some. If there is intersection, then this is true for all. Since here it is union, so we take for some n greater than equals to a. So clear, Ek is a set of all those x belonging to E where fnx minus fx mod is greater than equal to epsilon for some n greater than equals to k. I have already told you that Ek plus 1 will be a subset of Ek because k plus 1 in case of k plus 1, here n is starting from k plus 1. In case of Ek, n is starting from k. So clearly this is a subset of Ek. Now also for each x belonging to E, there must be some set Ek such that x does not belongs to Ek. Now why? Let if possible x belongs to Ek for all k. Then for given fixed k, we must have mod of fnx minus fx is greater than equals to epsilon for some n greater than equals to k. We just apply the definition of Ek. What we want to show that x does not belongs to Ek for each x. belonging to E. But we suppose the contrary part, that X belongs to Ek for all K. Now we apply the definition of Ek. Ek is the set of all those X belonging to E where this value is greater than equal to epsilon for some n greater than equal to K. Okay, so you will get this thing. Now if this thing hold, it means fnx does not converges to fx at some x. If this value is greater than equal to epsilon for some n greater than equal to k, so by definition of convergence, it means this does not converge to fx for some x, but that lead to be contradiction because it is given that this sequence converges to fx for each x. So that means our supposition is wrong. So it means there must be some set Ek. For each x belonging to E, there must be some set Ek so that x does not belong to Ek. So what are the observations? First of all, it is a decreasing sequence. Secondly, at least one point corresponding to one point, we always have a set Ek such that x does not belong to Ek. Means if we take the intersection of all these Ek, we will get phi set. Now once again see, if it is not phi, it means there is a point which belongs to each Ek. Means we get this condition. Means we get fnx which does not converges to fx. So again we get contradiction. So what we have Ek. It is a decreasing sequence of measurable sets for which this intersection is phi. If this intersection is phi, it means measure is 0. Okay, if this intersection is phi, so that means measure of En will be 0 for n going to infinity. Now by applying the definition of convergence limit, what we have, for given delta greater than 0, there exists positive integer n such that measure of Ek is less than delta for some k greater than equals to n. This is by the definition of convergence. What is the definition of convergence? A sequence an is set to converging to L if limit n going to infinity an is L, or for some epsilon mod of an minus L is less than epsilon for all n greater than equal to n. So now in this case our L is 0, sequence is en, measure of en. Okay, so if this limit is 0, it means this minus this is less than delta for some k greater than equals to n. So if in particular, if we choose k to be capital N, then measure of En is less than delta. Call this En set as A. So first we get a subset of E with measure of A less than delta. Right? Now apply the definition of En. What is our En set? It is a union of n varying from capital N to infinity of Gn. Means it is a set of all those x belonging to E where the mod of fnx minus fx is greater than equal to epsilon for some n greater than equals to capital N. So we get this. So measure of En is less than delta means measure of this set is less than delta. Right? If measure of this set is less than delta, it means E minus A set is a set where mod of fnx minus fx is less than epsilon, or for some m will replaced with for all n. Just take the reverse of this, complement of this. we have to write E minus A means E minus En. If En set is all those points where this is greater than equal to epsilon for some n, so E minus A set will be that set which contains all those points of E where fnx minus fx is less than epsilon. For some will be replaced with for all n greater than equals to capital N. Right? It means this thing hold for all x belonging to E minus A and for all n greater than equals to capital N. So this thing we have to prove that whenever we have a pointwise convergence sequence which is defined on a measurable set E with finite measure, then we always have a subset of E with very less measure, and on all those points which are complement to this set A, the sequence is converging uniformly. Fnx minus fx is less than epsilon for all x belonging to E minus A simultaneously. So this gives us a relation between the pointwise convergent and uniform convergence. Here it is on E, here it is on E minus A. So for all E minus A, the sequence is converging uniformly. Means we discard those points where it is not converging uniformly. We discard those points having the measure very, very small. Okay, thanks.